I'm back, baby.
Hello world and welcome back to Mathematics. After my year-long hibernation, I am back to spread mathematical cheer. Is this just because I'm bored and in lockdown with nothing better to do? It's hard to say, so let's just get on with the video, shall we? Alright, today we are looking at what's called the birthday paradox. We're going to start things off with a question for you. The question is, how many people would you need to have in a room before there is a 50% chance that two people in the room have the same birthday? Okay, so we want to know the minimum number of people you need to have in the same room for there to be a half chance that you've got at least two people that have a matching birthday. I'll give you some options, okay? Your first option is 183 people. Option B is 88. Option C is 47, and your last option is 23. Have a think about which one of those four makes the most sense to you. Maybe ask the people around you and see what they think. Okay, so the answer, which may surprise a fair few of you, it surprised me when I first heard this, is 23. Which seems like a very small number of people given that there are 365 days in the year, yeah? I know when I asked my housemates this, they both said 183 because that's roughly half of 365, so that sort of made sense to them. But when I told them the answer was 23, this was their approximate expressions. All right, so I swear to you the answer is 23, and today we're just going to do a quick video sort of explaining why this is the correct answer. And yeah, believe me, the maths does check out, so let's get stuck in.
I can explain. Let me explain.
Okay, now some people may say that this doesn't really seem like a paradox because I know a lot of people, when they hear the word paradox, they think of people going back in time and killing their own grandfathers to create sort of impossible scenarios. But the actual definition of what a paradox is just something that seems absurd or impossible, and then when you sort of take a closer look, it seems that it may actually be true, which is what this definitely is, okay? All right, so to make sense of this paradox, we need to have a few important mathematical concepts under our wing. So let's have a look at those before we can sort of start to tackle the actual problem.
Why don't you explain this to me like I am an 8-year-old?
Okay, so to start off, we're trying to find the probability of an event occurring, and it's a pretty complicated event. So there's this cool trick that we use in mathematics for questions like these, and it's essentially just working backwards, okay? Instead, sometimes it's much easier if you want to find the probability of an event not occurring, okay? The reason for this is we know that these two events together are going to make 100% chance. So if we can figure out the probability of an event not happening, we can take that away from 100%, and then, hey, you've got your answer easy peasy, okay? Some more maths we need to wrap our heads around to make sense of this is the idea of multiple events happening one after another. So a couple quick examples for you. If I had a standard 6-sided die like this, what would the probability be that if I threw it, it would land on a 4? So hopefully you know that there are 6 sides and a 4 is 1 out of 6 options. So that's our probability. It's a 1 in 6 chance. Okay. Another simple one for you. If I was going to flip a regular Australian coin, or any coin really, what is the probability you would see this lovely portrait of our darling Queen Elizabeth? So because we have 2 sides and Her Majesty's on one of them, it would be a 1 in 2 chance. Okay. Now the question for you is, how would we find the probability of doing both of these events one after another in succession? What would be the probability of rolling a 4 on a die and then immediately after that flipping heads on a coin? Okay, some of you may already know the answer to this. If you want to find the probability of consecutive events, all you need to do is just multiply the probabilities. Okay, so 1 out of 6 multiplied by 1 out of 2 gives us 1 out of 12. That tells us we have a 1 in 12 chance of rolling a 4 on a die and then immediately afterwards flipping heads on a coin. Okay? Now we have everything we need to sort of tackle this paradox and try and make sense of it.
Why don't you explain this to me like I'm 5?
Okay, so let's go back to our original problem. So reminder, we had, it was 23 people in one room. We are trying to find the probability that any of those 23 people are sharing a birthday. So at least 2 people being born on the same day. As I mentioned, we're going to be a bit sneaky and we're going to work this question backwards, and we are instead going to find the probability that this doesn't happen. We're going to find the probability that none of these 23 people were born on the same day. To make the maths a bit more friendly, we're going to just forget about leap years and just work off 365 days, okay? All right, so here we go. In our room, first person walks in. I don't know what their name is, I don't care. All I know is that they have a birthday and it's on one of the 365 days, okay? Now, person 2 walks in and we're asking ourselves, what's the probability that the second person has a different birthday to the first person? Well, there's a 1 in 365 chance that they have a matching birthday, which means there must be a 364 out of 365 chance they have a different birthday, okay? Now the third person walks in. And again, we say to ourselves, well, the probability that he or they, pardon me, are born on the same day as either of these 2 people, well, that would be a 2 out of 365 chance. So the probability person 3 has a different birthday again is going to be 363 out of 365. Okay, a couple more people walk in and we're starting to see a pattern. Each time the number on top takes 1 step down, and so on and so forth. I'm going to keep this going until we have another 22 people down the line, so we have 23 in total. Now, important to note that these probabilities that you can see here as fractions, these are all individual probabilities for each individual person. Reminder that we want all these events to happen consecutively. We want the first person to have a different birthday, and then the second and third and fourth and fifth. Okay? Like we saw with the coin and the dice, when you want 2 things to happen in succession, you need to multiply their probabilities. So we're going to do this. Okay? This is going to get us the probability of all these events happening in a row, which is what we want, because we want all of them to not share a birthday. Okay? So if we keep the pattern going down, like I said, we're going to need another 22 people. So we have 23 in the row in total. So if we take 22 steps down, we eventually get down to 342. Okay? So here is our expression that we need to just sort of tidy up a bit. So combining it all into one fraction, on the top we have 364 multiplying each step down until we get to 342. And on the bottom we have 365 multiplying by itself 22 times. So we can tidy this up a bit. We can write the bottom as 365 to the power of 22. Okay, because I don't want to type all these numbers into my calculator. I want to save a bit of time. Now up top there is another shortcut which not many people know. What this is called when you're multiplying and stepping down each time, it's actually called a permutation. Okay, it's a fancy word and there's a fancy button on most calculators for it. It looks something like this. This is a permutation of 22 objects from 364 in total. Okay, so that is essentially that, but just done really quickly. Okay. All right, if we feed those numbers into our favorite scientific calculator, it should give you an answer of about 0.4927, which as a percentage would be about 49.27%. So we have just proven that there is a 49.27% chance that none of these 23 people share a birthday. So what does that mean about the other 51%? Well, that means that that is the probability that any of them, any 2 at least, are going to have a matching birthday. Okay, so again, there's a 49% chance that none of them share a birthday. So there must be a 51% chance that at least someone in there shares a birthday with someone else. Okay? So there you go. It is true. It has been proven. So next time you're in a room with 23 people, you'll have to let me know because I don't have 22 friends. But next time it happens for you, just do a quick scan and say, hey, anyone got a matching birthday? About half the time it will happen, probably. Okay, if you made it this far, thanks so much for watching. I really appreciate it. I'll see you next time, which will probably be never. All right, goodbye.